Hey y'all, today we're going to be talking about logarithmic integration. So logarithmic integration is, that natural log. Now, when I say logarithmic integration, it's not actually integrating natural log functions. Logarithmic integration is more of the integral of functions that become logarithms. So we're not really going to be integrating the natural log. Let's kind of see what I mean by that. So first and foremost, we want to recall the differentiation rule for our natural log function. So if we recall, the derivative of the natural log of u, or of some x, something inside of the natural log, is 1 over my original function times the derivative of the inside. So remember, our natural log was a chain rule. We derived the outside, we derived the natural log, we kept the inside the same, we kept that u the same by sticking it in the bottom of the fraction, and then we derived and multiplied by the inside. So 1 over u times u prime, or we also just write it as u prime over u. So finding each of these derivatives, if I find the derivative of natural log of 2x, y prime would be 2 over 2x, which would just be 1 over x, because it's the original function on the bottom, derivative on the top. Okay, natural log of 3x squared minus 5, y prime would be equal to 6x over 3x squared minus 5. So super, super easy. Okay, should be familiar. So knowing that, if I know that the derivative of the natural log is equal to that u prime over u, or that 1 over u, then what would the integral of du over u be equal to? Well, just as kind of a reminder, du is really just the same thing as the derivative of u, which is u prime. So really what I'm asking is, what's the integral of u prime over u? Well, the integral of u prime over u is the natural log. And we add in that absolute value, essentially because we don't want to have negative numbers in our natural log, because negatives in our natural log makes our natural log undefined, and we don't want our new function to be undefined. So just kind of, that only comes into play when you actually plug into your function after you integrate. But just know you do need to add in, number one. And number two, that you will only see, like on multiple choice questions, they'll all automatically have that absolute value in there. Okay. But let's talk about this a little bit more. So number one, we have the integral of 2 over x dx. Okay. So from first glance on this one, it doesn't really look like anything is necessarily trapped. Okay, but I do have a constant of 2, so I can, before I even integrate, I can take that 2 out, so then this becomes 1 over x dx. Okay, so that looks exactly like our u prime over u. The derivative of x is 1, so it is its derivative over itself. So when I see that, I can really just make the jump straight to applying my rule. So this becomes 2 natural log of the absolute value of x plus c. So notice that I didn't even have to take a u, because I didn't really have anything trapped. I knew I wasn't going to get an extra constant from my derivative of x. So I can kind of just make that jump, which is the nice thing about logarithmic integration. It's real basic logarithmic integration. You can just integrate without having to do a u substitution. But we make sure that we denote it using u, so that we know that it is always technically u substitution. We just don't show all of the steps. So let's look at another example with number 2. The integral of 1 over 4x minus 1. Okay, so this time, derivative of 4x minus 1, that would be 4. I don't see 4 in the top, so this is not perfectly my u prime over u. So even though I don't necessarily need an x to get canceled out, I still have to take a u here, because I have to account for that 4 not being in the top. Okay, so my u sub in this one would be 4x minus 1. Actually, I'm going to do that in a different color just to make it a little easier to denote. So my u sub for this one, u is equal to 4x minus 1, which means du is equal to 4 dx, which means du divided by 4 is equal to dx. So then before I integrate, I can make any necessary changes. So this becomes 1 over u times du over 4, which becomes 1/4 1 over u times du. So see what I mean by accounting for that extra constant? Just because I don't need an x term to cancel out, I still have to do u substitution here because I know that derivative is going to give me an extra 4 that I have to account for. So if I didn't do a u and I just went straight to applying my formula, I wouldn't get that extra 1/4 out front. Okay, but from here, integral of 1 over u du, or as we say, du over u, which is the same thing as 1 over u times du, is equal to 1/4 natural log of the absolute value of u plus c. And as a final step, I can just plug everything back in, simplify where I need to. So this becomes 1/4 natural log of the absolute value of 4x minus 1 plus c. And of course, I can write that as 1/4 times. You could write that as the natural log of 4x minus 1 over 4. Either one is fine. All right, looking again, number 3, we have the integral of 3x squared plus 1 over x cubed plus x. So this one, even though it looks a little bit more complicated, notice derivative of x cubed plus x is equal to exactly 3x squared plus 1. So this one actually is, in its exactitude, u prime over u. So I can once again just go straight to applying my formula. I know this one is equal to the natural log of the absolute value of x cubed plus x, because it's the natural log of the absolute value of u. Whatever I would have taken out as my u substitution is what's going to end up here. And then, of course, tacking on my plus c because it is still an indefinite integral. Okay, let's look at another one. Ooh, trig with number 4, which we never really like trig. Trig's not really quite our friend, but if we know our trig, we know the derivative of tangent is secant squared of x. So this is perfectly u prime over u. So the integral of secant squared over tan, I can apply my formula directly, just becomes the natural log of u, so the natural log of tan x plus c. Okay, so I'm going to give you all a little bit of practice. So go ahead and try 5 and 6 on your own. So you can go ahead and pause me, and then I will show you the answers and talk about them here in about 5 seconds. All right, y'all. So let's talk about each of these. So on number 5, our u is x squared plus 2x. Derivative is 2x plus 2 dx. So we get du over 2 times x plus 1. And just like I showed you on that one, on our last u substitution notes, because I know I need x plus 1 to cancel out, I went ahead and took a GCF of 2 out so I could get that x plus 1s to cancel out. So when we plug back in, x plus 1 cancels out. We get that extra 1/2 in front, integrate, and we get 1/2 times the natural log, absolute value of x squared plus 2x, and then plus c. Number 6, we don't need anything to cancel out, but we do have more than just x going on the bottom, so I need to account for that. So 3x plus 2 is our u, which gives us that extra 1/3. When we plug in, we get 1/3 times the integral of 1 over u du, which gives us 1/3 natural log of u plus c. Plug in, 1/3 natural log of the absolute value of 3x plus 2 plus c. Okay, hopefully this is starting to seem pretty familiar, make a lot of sense. Okay, last kind of new skill we're going to learn today is our integrals of all of our other basic trig functions. So remember, we've talked about going backwards with all of our trig derivatives. So sine, cosine, secant, cosecant, tangent, and cotangent. We know all their derivatives, so if we see any of their derivatives, we can integrate backwards. Well, we can also integrate all of the other trig functions, which would be tan, cotangent, secant, and cosecant, which aren't the derivatives of other basic trig functions. So think about it. Only sine and cosine are each other's derivatives. Tan, cotangent, secant, and cosecant, when you derive them, all become more complicated or different. Okay, so to integrate just tangent, cotangent, secant, or cosecant, we actually get these crazy, weird natural log integrals. And you're probably like, Mr. Starbone, am I supposed to memorize that? And my unfortunate answer is yes, you are supposed to memorize these. Okay, I'm going to show you on number 7 obviously applying the rule. And then I'm also going to show you why the integral of tangent becomes the negative natural log of cosine of u plus c. Okay, so I'm not just going to leave you hanging and be like, Mr. Arbone, what is this? I'm going to actually show you why this happens, okay? So on number 7, we want to find the integral of tan x dx. Well, if you know your formula, you can make this super easy and just say, well, I already know that integral. It's the negative natural log of the absolute value of cosine of x plus c. Simple, Mr. Arbone. Easy. Okay, now let's actually talk about, well, what if we didn't know that formula? So let's just say you don't memorize your formulas. Well, you should, if you don't have your formulas memorized, hopefully you have your trig identities memorized. Not exactly counting my blessings on that one, but, you know, a teacher can hope. So if you know your trig identities by heart, then you might know that you can change tangent of x to be sine of x over cosine of x. So I can change this to be the integral of sine of x over cosine of x dx. Hey, now what does that look like? Well, we know the derivative of cosine is negative sine. So while the sine isn't quite right, the derivative of cosine is on top. So that looks a lot like u prime over u. So let's go through the full process this time. Let's take our u. So our u would be cosine, which means our du is equal to negative sine dx, which means du divided by negative sine of x is equal to dx. So plugging back in, we get the integral of sine of x over u times du over negative sine of x. We get those sine of x's to cancel out, but we end up with this extra negative in front. So that becomes, haven't integrated yet. So that becomes negative times the integral of 1 over u du, which, once we do that, then we can integrate. So that becomes the natural log of u. So negative natural log of the absolute value of u plus c. And then plugging back in my u, which was cosine of x, we get negative natural log of the absolute value of cosine of x plus c. So regardless of if you have your formula memorized or if you just know your trig identities, you can still find this integral. Okay, but I just wanted you to kind of see where those formulas came from. I didn't just pull them out of nowhere. There is real math and real calculus behind them. But if you know those formulas, awesome. These are super easy. If you ever forget the formulas, you can use any of your trig identities to also find all of these answers. Okay, so just kind of keep that in mind. All right, number 8, we want to find the integral from 0 to pi over 4 of the square root of 1 plus tangent squared of x dx. Okay, so right off the bat, square root of a whole bunch more, so it's probably u substitution. But even with that, if I took out 1 plus tangent squared of x as my u, derivative of that would be 1 would go away, but tangent squared of x would become some mess of like 2 times tangent x times secant squared of x, and then I'm not going to get any of that to cancel out. So I can't do my u quite yet, but I can think, well, I do know that 1 plus tangent squared of x is equal to secant squared of x. So before I do any extra hard work, I can change out my formula just a bit. So using a trig identity, I can replace 1 plus tangent squared of x to be secant squared of x dx. Okay, so from here, what's the square root of secant squared of x? Well, the square root of something squared is just equal to the original, or what's under the function. So this becomes the integral from 0 to pi over 4 of just secant of x dx. Okay, now I don't actually have to do a u sub at all because secant of x actually has an integral formula, and it's that natural log one. So my integral of secant of x is equal to the natural log of secant of x plus tangent of x plus c. Okay, So now, without even having to do an integral rule, I can integrate this to get the natural log of the absolute value of secant of x plus tan. And if you just notice, I don't have these memorized. So while I tell you you should have them memorized, I check on them all the time if it makes you feel better. Okay, so the natural log of the natural log of secant of x plus tan of x, and I'm evaluating it from 0 to pi over 4. Okay, so even though this is fundamental theorem, and this is in a U substitution notes, because I didn't actually have to do a U sub, I didn't actually have to do a change of base. So just something to keep in mind is if you can avoid doing a U substitution by doing some simplifying first, then you can avoid also having to do a change of base. So nice little things how some of your math skills can come in handy for you. Okay, so from here I'm just going to plug everything in. So this is equal to the natural log of secant of pi over 4 plus tangent of pi over 4 minus the natural log of secant of 0 plus tangent of 0. And then from here, natural log secant of pi over 4, that is 1 over the cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So reciprocal of root 2 over 2 is just root 2. So this becomes the natural log of the absolute value of root 2 plus tangent of pi over 4 is sine over cosine. Sine and cosine are both root 2 over 2. So this is just 1 minus natural log secant of 0. Once again, 1 over cosine of 0. Cosine of 0 is 1. 1 over 1 is just 1. And then tan of 0 is sine over cosine. So sine of 0 is 0. Cosine of 0 is 1. 0 over 1 is just 0. So this is equal to the natural log of the absolute value of root 2 plus 1 minus, all of this right here is just the natural log of 1. And if you know anything about your natural logs, the natural log of 1 is just equal to 0. Which we'll save ourselves an extra writing step because this is just equal to 0. So minus 0 is just what I got left. So another little thing as we're getting into logarithms, which we use these a little bit with derivatives, but now we're using it even more with integrals because we're going to have to evaluate these big, long logarithms with some of our natural log integrals, is knowing your log properties, okay? So that's a log property, noting that the log of 0 is equal to, the log of 1 is equal to 0, okay? That's another little log property. So another little pre-cal skill, hopefully you have memorized. If not, just Google real quick, logarithm properties, and they're all going to pop up for you. Okay. Number 9, find the average value of tan of x on the interval from 0 to pi over 4. Okay, so average value, remember, is just an integral that we're multiplying by 1 over b minus a in front. So 1 over b minus a is just 1 over pi over 4 minus 0. And then that's time the integral from 0 to pi over 4 of tan of x dx. So from here, I can go ahead and integrate. 1 over pi over 4, that's just 4 over pi, because I just take the reciprocal of pi over 4. And then integral of tan of x is the negative natural log of the absolute value of cosine of x. And I'm evaluating that from 0 to pi over 4. So once again, not having to take a U sub, didn't have to do a change of base. So from here, I can just plug in my numbers. So I still have my 4 over pi in the front. Inside, I have negative natural log of the absolute value of cosine of pi over 4. Minus the negative is the same as plus the natural log of the absolute value of cosine of 0. Then from here, Cosine of 0 is equal to 1. Cosine of pi over 4 is root 2 over 2. So I get 4 over pi minus natural log of the absolute value of root 2. Sorry, root 2, not root 3. Root 2 over 2 plus the natural log of the absolute value of 1. Now, we just talked about this. Absolute value of 1 is just equal to 0. So realistically, this is just negative natural log of root 2 over 2 in front, which I can multiply by my 4 over pi. So I get negative 4 over pi natural log of root 2 over 2. And I can leave the absolute value of root 2 over 2, but I can also just, absolute value of positive root 2 over 2 is just root 2 over 2. So it doesn't really matter if you leave it in the final answer or not. And of course, because I'm doing this without a calculator, it's supposed to be messy like that. It's supposed to be negative 4 over pi natural log of root 2 over 2, okay? I can't simplify that without a calculator, so it's going to be messy like that. I could technically, change that square root of 2, try to, take some multipliers out, split it up into multiple logs, but that's not simplifying. That's just making it, moving numbers around. So just leave it like that. Last but not least, y'all, and I'm going to try and not make this too long, number 10. So we're evaluating from 1 to e to the 4th of 1 over x natural log of x. Okay, so right off the bat, we have 1 over x natural log of x. Okay, so it doesn't necessarily look like a u sub, but it looks like a u prime over u. It looks like a natural log integral right off the bat. So we kind of have to think about what we're going to take as our u. And just like I said, with our basic u subs, it can be really easy to identify u. As they start to get more complicated, you kind of have to play around and think about different things you could take as your u. So, okay, if I took x as my u, well, derivative of x is 1, so that's not going to get anything to cancel out. And you'd have to take x in both of these out, so you just end up with 1 over u times natural log of u. So taking x out as your u doesn't do you any favors, okay? If you took out x times natural log of x, okay, well then you're going to have to do a product rule derivative for that. So you're going to end up with a whole bunch of extra x's, but you're not going to have any left over in your problem to actually get to cancel out. So our only other real option to take as a u is just natural log of x. And if we take natural log of x, derivative of natural log of x is 1 over x, which might end up getting the other x that's left over in the problem to cancel out. Let's try it, because sometimes u sub is all about trial and error. So if we take out as our u, natural log of x, so u is equal to natural log of x, and that means du is equal to 1 over x dx, which now instead of dividing over, I can multiply over my x. That gets du x is equal to dx, or x times du, whichever way you want to write it. Okay. Now, because I did a u substitution of a definite integral, what other thing do I have to do? I also have to change my base. So I also need to do u is equal to the natural log of 1, which gives me 0, because remember, natural log of 1 is 0, and u is equal to the natural log of e to the 4th, which, if we remember our log rules, base e, that cancels out. So u is just equal to 4. Well, that's a nice new integral, nice new base of 0 to 4. So plugging this into my integral, we get the integral from 0 to 4 of 1 over x times u times x times du. Because I replace dx with x times du, I replace natural log of x with u, and then I still have that x in the bottom of my problem. Well, right off the bat, we see that x and x actually cancel out. So we're going to be left with just the integral from 0 to 4 of 1 over u du. So now this is something that I can integrate. I can apply my natural log. Okay, so the integral of 1 over u du is equal to the natural log of the absolute value of u And I'm evaluating that from 0 to 4. So from here, this becomes the natural log of the absolute value of 4 minus the natural log of the absolute value of 0. And then as a final answer, natural log of the absolute value of 4 is just the natural log of 4. Natural log of 0, some of you might have perked up right there because like, wait, Mr. Arbone, there's no such thing as the natural log of 0. It doesn't exist. You're correct, okay? Which isn't quite the same thing as 0, but when we're evaluating to find an actual area, it's not like all of the area we found didn't exist. It's just some of the area we found didn't exist. So we can just ignore it in our final answer, which you're probably like, Mr. Arbone, that's not an acceptable answer. But it is for now until you get into more advanced math and you can talk about why or how to include undefined area. But for right now, we're just going to ignore its existence. So if you get undefined for your log, but you still have something else that's left over in your answer, you can just ignore that undefined as negligible. Okay, and that is logarithmic integration, y'all. So as you can see, it shows up in lots of different forms with trig functions, with definite integrals, with more basic ones, with ones with logs, and then you integrate by log. So it can be very versatile. And hopefully on your fundamental minor grade, you started to see a bunch, but go ahead and work on the practice, and then we'll talk about this more in class.